Sorry, let me get the screen share up and running. As you can see, we're really on top of things after the long weekend, but yes, hopefully everyone had a good July 4th, saw something fun, or went to sleep to avoid the fireworks. But yeah, here we are, CS 161, Lecture 8, PRNGs and Diffie-Hellman key exchange. Woo! Okay, that's enough of that. Okay, so just getting right into it. I don't think we have an announcement slide this time, but just as a reminder, project 1 is due tonight, Tuesday night, and homework 2 is due tomorrow. Just a heads up. We are kind of getting close to the deadlines. If you do need extra time because something came up over the weekend, or there's some extenuating circumstance, or maybe you're a DSP student, that's totally fine. So all you have to do is go fill out the extensions form. It's cs161.org/extensions, and just let us know why you're requesting the extension, and then we can get back to you. So we'll try our best to be lenient with extensions and understanding. So if anything really has come up and you need the extra days, feel free to ask. And if you need extra days, remember you also have slip days. So you are allowed 3 slip days, so you can turn in this project 3 days late if you want. Of course, then you don't have slip days for the rest of the semester, but it's up to you. Okay, I think those are the only announcements. And homework 3 will probably come out when? Today? Okay.
Today. We're trying to go for our Tuesday, Monday schedule. It's just that it was messed up by the 2 Monday holidays. So hopefully we can get back on track with that.
Homework 3 today it is. So that's our invisible announcement slide. Now, last time we talked about hashes. So this was before the long weekend. We talked about how hashes are functions that map an arbitrary length input. It can be as long or as short as you want as the input, and the output is fixed length, so it's always n bits long. Then we talked about how the output is deterministic. So if I hash the same thing 10 times, I get the same output 10 times. And it's also unpredictable. So if I change 1 bit of my input, the output completely scrambles up in ways that I can't predict. And then we talked about there are 3 security properties that we're looking for in a hash. We want hashes to be one way. So given an output, you can't find any input that hashes to the same output. Second preimage resistance says given an input, you can't find another input that hashes to the same output. And collision resistance says given any pair, you can't find any pair of inputs that hash to the same output. So those are the 3 properties we want. Then we talked about how some hashes might be secure, but still vulnerable to another attack called a length extension attack. So given the hash of a value, but not the original input, you can actually construct the hash of that same value concatenated with something else. And I think homework 2 shows you an example of how that might happen. So some hashes are vulnerable to that and some aren't. And then we talked really briefly about there's kind of a lowest hash scheme application. So if you're a reporter or a journalist and some hacker comes to you and says, I've stolen 150 million records, it turns out you can use cryptographic hashes and their unpredictable random properties to prove that the attacker really has stolen 150 million records and is not exaggerating. So even if you never touch security again, it turns out cryptographic hashes do have interesting other applications. And then we talked about how hashes by themselves don't provide integrity unless you can publish the hash securely. So if you're Mozilla Firefox or something and you're publishing Firefox on your website and you also publish the hash of Firefox on your website securely, and you know that nobody can change the hash on your website, then maybe you're okay. But if you're in the Alice and Bob setting, which is the one we're studying, then remember, if Alice sends a message to Bob and Mallory is on the channel and can tamper, then hashes don't provide integrity. Because what does Mallory do? She just swaps out the message to whatever she wants and then just swaps out the hash because hashes don't have keys, so anybody can hash a message. So that was hashes. And then we talked about how, well, hashes don't give us integrity, so let's, and the reason why was because there were no keys. So let's add a secret key to the hash and create a function that does provide integrity. So that's called a MAC. And again, a MAC takes a message of any length that you want and a secret key, and the output is a tag on the message. And the tag was like the seal. So if Mallory changes the message, the seal breaks and Bob knows that it's been tampered with. So those were MACs. And then we said a secure MAC is unforgeable. And the definition was EUCPA, which is kind of a game. But the definition basically said, we allow Mallory to trick Alice into creating a bunch of Macs that she chooses. So Mallory tells Alice, Mac this. And Alice is like, okay, I'll Mac it and give you the Mac. And she can repeat this a bunch of times. But even if we allow Mallory the power to do this, she can't create a valid Mac on a message that she's never seen before. So that was the definition. And basically it just says, if Mallory doesn't know the key, she can't create her own Macs. That's the intuition. And then we showed you an example of a Mac algorithm, which was HMAC. And HMAC basically used a hash to create a secure Mac. So we hash the key and the message together, and that provides integrity. And we have to do it in a very careful way to prevent things like length extension attacks. And then finally, we noted that Macs don't provide confidentiality because Macs are only designed for integrity and authenticity, kind of. So they do not do anything to secure your message. They output a tag on your message, but they don't encrypt your message. So then we talked about authenticated encryption, which was a way to give us both confidentiality and integrity on a message. So let's have both together. And there were two approaches that we thought of. So the first one was, let's say, I have schemes that give me confidentiality. Those are the block ciphers and the chaining modes. We also had schemes that give us integrity. Those are Macs. So let's just combine them together. But you have to be very careful because there were two different ways to do it. One way was I will take the message and I will Mac the message and I will encrypt everything. So that's called Mac then encrypt. Or I can take the encryption and then Mac the ciphertext, and that's called encrypt then Mac. And we talked about how because there are some really subtle timing attacks, we have to use encrypt then Mac. Because if you screw up, it's much better to be in the encrypt then Mac scenario so that you're not open to attacks. And I don't think it's on this slide, but remember that you don't want to reuse keys. So you notice how we use K1 for encryption and K2 for Macs, because if you have two different algorithms, you want to use different keys. If you reuse keys, there's a whole category of attacks that now you have to think about, and I don't want to think about them. So I will just never reuse keys and I can ignore them. Now, the second approach is called authenticated encryption with additional data, which is a lot of words, but basically it's an encryption mode that you designed from scratch that provides everything at once. So as soon as you design it, it gives you all of them together with a single algorithm. Now, the benefit here is if you use it correctly, you have all three properties given to you right away. That's great. And you only need to use one algorithm. The downside is if you mess up and you use it incorrectly, guess what? You lose confidentiality and you lose integrity and authentication. So it's a useful category of algorithms, but it's kind of high risk. So you have to make sure you're using it correctly. So that was last time. So today we're done with symmetric encryption for the most part. We talked about how we guarantee integrity and confidentiality and authenticity with symmetric keys. So today we're gonna kind of switch gears and talk about two kind of side topics that are important for symmetric key encryptions. So the first one is, well, symmetric key encryption schemes need randomness. There were a lot of applications where we needed something that was random. So we're going to talk about how we securely generate random numbers. And then we also talked about how last week we kept assuming in symmetric key, Alice and Bob share a secret key. So somebody has come down and blessed them with some secret keys that no one else knows. And today we're actually going to dig and see how they do that. And that'll be the second half of the lecture. So that's the plan for today. Okay, so the first thing, the first half is all about pseudo-random number generators, which is kind of a side topic because, again, it's not really an algorithm that provides confidentiality or integrity or authentication. It's kind of a helper function because symmetric key encryption requires a lot of randomness. So now we're going to investigate how you provide randomness. So randomness, it's very essential. It comes up all the time. When I need a symmetric key, all those key generation algorithms just said, give me a random key. So that was something that required randomness. We also said in block cipher modes, I need IVs and nonces, which are random values, and I have to use a random value for every encryption. So randomness comes up a lot. And there's another application that we'll see in a little bit called universal unique identifiers. And there are a whole bunch of other applications that come up later. But already you can see randomness is everywhere in cryptography. And if you can predict randomness, things can really fail badly. So we have to, not only do we have to generate random numbers, but we have to generate a random number securely. So we can't allow attackers to predict future randomness, because that's dangerous. And we also have to define what does it mean for random numbers to be secure. So those are all things we have to solve. So to solve that, first we're going to talk really briefly about entropy. And all we're going to say here is that random usually means random and unpredictable. So for example, I want to generate a secret bit string, zeros and ones, that the attacker cannot guess. So this could be a secret key, or it could be an IV or something. I don't want the attacker to be able to guess what my secret string is. So what I can do is I can toss a fair coin. So the coin lands on heads and tails with equal probability. So I toss a coin, it's heads, so I write a 1. I toss a coin, it's tails, so I write a 0. I toss it again, I get tails, so I write a 0. And I do this until I get the bit string that I want. So that's really hard to guess because the outcome is 50-50, right? If I ask you to guess, I toss a coin and I say guess, you only have a 50% chance of guessing right. So the outcome is very hard to guess. And we can formalize this with something called entropy, which is a measure of uncertainty. So how hard is it for the attacker to guess what I'm doing? Now, high entropy means that the outcomes are very unpredictable, and that's what we want in cryptography. And in particular, the uniform distribution has the highest entropy, so every outcome is equally likely. So for example, tossing a 50-50 coin is great because the attacker has a really hard time guessing what the outcome is. But what if I said, I'm going to generate my secret key by tossing this biased coin? This coin comes up heads 99% of the time, and it comes up tails 1% of the time. So it's almost always heads. Well, now the attacker has a pretty good chance of guessing my bit string, right? They can guess lots of heads, which I guess are ones, and that'll give the attacker a very good chance of guessing. So what I want is I want the attacker to be unable to guess my coin tosses. So I want to sample things from the uniform distribution, which just says every outcome is equally likely, because that's the hardest for the attacker to guess. If you take classes like, I think CS 170 talks about this, maybe some other ones, and maybe just some crypto classes, they dive a lot more into entropy. But for this class, all you really have to know about entropy is we want things that are unpredictable. And the most unpredictable thing you can think of is fair coin tosses, because every outcome is equally likely. And I think that's as far as you have to know. Okay. So as an example of what could possibly happen if I use poor entropy or I use something that's predictable, well, here's an example. This is from a Bitcoin application. So we'll talk about Bitcoin a bit later, but Bitcoin users use a randomly generated private key to access their money. So if you have the private key, you can access your money. You can withdraw money, you can spend the money. So it's very important that this private key is unguessable and it's unpredictable because it's randomly generated. So what can go wrong? Well, someone at some point edited this Bitcoin library and they improved the algorithm, or improved with quotes the algorithm. And what happened was they actually accidentally reduced the amount of entropy used to generate the private keys. So it used to be very hard to guess, but somehow their fix to this program made it easier to guess the private keys. And because it was easier to guess, what does the attacker do? The attacker guesses the keys and they have a very good chance of succeeding. And so they brute force the keys and now they can steal your money. So that was a mistake. And I don't know why they called it this, but it's called improvement. So they didn't even spell the commit message correctly. So this was a mistake. So the safest thing we can possibly do is, if we don't want the attacker to guess what we're using, we can use true randomness. So let's generate numbers that are actually random. And the way we're going to do this is we're going to find a physical source of entropy, something that exists in the real world. So it's not software, it's hardware. So an example is maybe on my CPU, I have a circuit that's very unpredictable and the voltage changes randomly, and that's something that could be random. Maybe I can measure the user's interaction at a very fine time scale. So as you're typing, the computer can say, you press the key at this microsecond. And because you can't even measure microseconds, the microsecond at which you press the key is probably a very random number. It doesn't look predictable. There's no predictable pattern that you always press keys at a given microsecond. So that could be a random thing. And usually, if you combine a bunch of these together, you can get truly unbiased entropy. So sometimes some of these things are a little bit predictable. So maybe the CPU isn't perfect, or maybe human activity is a little bit biased. So what you need to do is you sometimes have to combine a bunch of different entropy sources to get truly unbiased high entropy sources. So maybe one of my entropy sources is very biased. It generates a lot more ones than zeros. And this entropy source generates a lot more zeros than ones. So I have to do something to combine them so that my true entropy source ends up being an equal number of zeros and ones, unpredictable. Okay. And generally, there's a lot of different ways to combine them. And I think you'll see some of those in discussion. But the high level idea is if I take lots of poor sources and I combine it with at least one good source, then I should be okay. So usually it's the sum of all the entropy sources that I have. Now, there are some issues with true randomness. So the first issue is it's expensive. To generate true randomness, I have to use a physical process, like a CPU circuit, or I have to wait for the human to type things. That's very expensive and it's very slow to generate. And like we said, there's often a lot of biases. So a lot of physical sources, like sometimes people use atmospheric noise or like random radio waves or something, or cosmic waves. Some of those are actually kind of biased for physical scientific reasons. They have more ones than zeros, for example. And that could be a problem because remember, if there are a lot more ones than zeros that come up, then the attacker has a better chance of guessing our secrecy, our secret random numbers. So as a kind of unusual example of true randomness, here's an exotic one for you. Cloudflare, which is a company that deals in security, they have a wall of lava lamps. So these are lava lamps. And lava lamps, I don't actually know how they work, to be honest with you, but they have this kind of flickering light and it flickers in very unpredictable ways. Yes, probably magic. So what they do is they have a video camera, they point it at the wall of lava lamps, and they use the lava lamps that are kind of flickering in random ways to generate randomness. So if the light kind of flickers to the left, it's a 0, maybe if it flickers to the right, it's a 1. And so you can use kind of these weird sources of physical entropy as well, as long as there's no way for the attacker to predict the way that the lamp is going to move around. So that's something you can use too. So there are lots of different ones, but the general takeaway is that they're kind of expensive. So very expensive and sometimes biased. So I don't want to have to generate an expensive number of random bits every single time I want to encrypt. I want encryption and decryption to be fast. I don't want to waste time flipping coins or staring at my lava lamps. So what am I going to do? I'm going to use a pseudo-random number generator. That's kind of a long word, and sometimes we just say PRNGs. But this is an algorithm. So the input is it takes a little bit of true randomness. So you give it some really physical random process output, random numbers. And then it generates a lot of output that isn't random, but it looks random. So sometimes it's called a deterministic random bit generator. I don't know why they have so many long names for this thing, but I guess there are quite a few. So the way this works is the first thing I do is I use my CPU circuit or my lava lamps or my keyboard pressing to generate some expensive true randomness. This is expensive, but I'll get a little bit of it. And then I will input it into the PRNG. The PRNG runs a deterministic algorithm. So it's, again, it's bit shifting, it's XORs, it's a deterministic algorithm, but the output is random looking numbers. So the algorithm is fast because it's all bit shifting and it's deterministic, and it's not actually generating random numbers. It's running a predefined algorithm. But if you feed the predefined algorithm with true randomness, the output should actually look as good as random. And this gives us a very quick and cheap way to generate random looking numbers. So one thing is PRNGs are deterministic. So the output is generated according to a set algorithm. So again, the algorithm is set in stone, but once you start generating output, it looks random. And if you're an attacker and you can't see the algorithm or the input to the program, to the PRNG program, the output is called computationally indistinguishable from true randomness. So what that means is, given a reasonable amount of computation power, so something that someone can do in modern days, an attacker can't tell whether this output is truly random or PRNG random. Someone asked, how is a PRNG different from a hash? So that's a very good question because some of these properties are things that we want in hashes too. Hashes want random looking output and they want should be unpredictable. But I think we'll talk a little bit about the differences a bit later. I think one main one is, I think as Nicholas said, if the hash algorithm doesn't have any secrecy or any keys to it. So I guess, what is Nicholas saying? He's saying, right. So because there's no secret key to it, if we're just using a hash to generate pseudo-random numbers, then the attacker, if they know the input, they can just hash the output themselves. I think that's one reason. The main reason I can think of to distinguish them is pseudo-random number generators are going to give us a lot of output. So I want a lot of random numbers from a small amount of true randomness. And hashes give us constant length outputs. So if I hash a number, I get n bits every time. But if I hash, or if I feed some randomness into a PRNG, I can get lots and lots and lots of randomness, way more than n bits. So to me, that's the main difference. But I think you're right that they're kind of similar. And in fact, you'll see how I can use hashes to build PRNGs in just a moment. Okay, so here's the formal definition of a PRNG. There are some different mathematical definitions, but for this class, this is the one that we'll stick with. So there are 3 different functions. There's one called seed. So this one takes in entropy, and this is truly random numbers, and it internalizes an internal state. So this algorithm, inside the algorithm, there are some variables maybe that have to be kept. So I use this entropy to internalize the internal state. And the input is some random bits, and there's no output. There's another function called reseed. So maybe I've generated some output, but then I get some new randomness that I want to add to the PRNG. So this says the PRNG is already running, but I'm going to dump in some extra entropy. So here's some extra randomness for you to use. So again, I input some truly random bits and there's no output. And the last thing is called generate. So this is how I actually generate bits. So when I call generate on the PRNG outputs lots of bits for me. So the input is just n asking for how many bits I want. And the output is that many pseudo-random bits. And these bits are deterministic. So they are generated according to your input, but they look indistinguishable from random. So the attacker can see these and they have no idea how to guess them because it's random. Great. And if needed, the generate function can update internal state as well. And sometimes you see a different definition where in addition to generating, you can also dump in extra entropy here, but it's up to you. Okay. And there are a couple of properties that we want. I think we talked about some of these already. So for correctness, I want the PRNG to be deterministic. So if I feed in the exact same entropy twice, the output is the same twice. So it is deterministic, but that's okay because the security property I want is it's indistinguishable from random. So if I give the attacker, here are some bits that were generated from a PRNG, here are some bits that were generated from just coin tosses, they can't figure out which one is which, and that's security. And we also talked about efficiency, which is that a PRNG should be fast because true randomness is expensive and slow, but PRNG output is fast. Okay. So we talked about this a little bit before, but again, if you have a whole bunch of different entropy sources, the total entropy is generally the sum of all your sources. So usually it doesn't hurt to give the PRNG a poor source of entropy. So all you have to do is when you start up a PRNG, whatever randomness you have available to you, just dump it in the PRNG. Maybe it's a good source that is unbiased. Maybe it's a bad source and it's very biased, but it doesn't matter because entropy sources usually add up. So whatever I have, just throw it in the PRNG. And again, usually if I have a lot of low entropy sources and I combine them, I can usually get some pretty good high entropy output. And in fact, even if I have a terrible source of entropy, it's zero entropy, the attacker can easily guess what it is. I can still throw it in and it shouldn't make my PRNG worse. So it really doesn't hurt to throw whatever you have into the PRNG, at least using the definition that we've provided. And reseeding is maybe right now I don't have the entropy, but later I receive more entropy. So if that's the case, I can also just take the more entropy that I get later and throw it in the PRNG. So it's kind of like a big blender, and anything that you have in the kitchen or the fridge or any randomness, just throw it into the blender and hopefully something tasty will come out. I don't think that analogy fully works, but we will go with it. Okay. So again, just whatever you have, throw it in the PRNG, and hopefully the output will be random. So we talked about this earlier. The PRNG is not truly random because, again, given the initial seed, I can actually figure out everything. So the seed is just another term for the input. So if the attacker knows the input, they can run the algorithm and get the output. So it's not really random, but if the PRNG is secure, then it's computationally indistinguishable. So we talked about this game earlier. The attacker gets two strings of bits. One of them is a truly random sequence. It was generated with coin flips or lava lamps. The other one is outputted from a secure PRNG. And if the attacker can't figure out which is which with probability greater than a half, then the PRNG is computationally indistinguishable from random, and so it's secure. And another equivalent definition, so this definition, you can prove that they're the same, but another definition that works is an attacker can't predict future output of the PRNG. So suppose today the attacker sees some PRNG output. Oops. The attacker sees some PRNG output, but given this PRNG output, they don't have the input, they just have the output. They can't predict if I generate 10 more bits or 20 more bits, they can't predict what those bits are. So these are equivalent definitions, and you can think of whichever one helps you better. But the idea is that this output just looks random. So even if I can see some output now, I have no idea what the future output will be. The next slide is blue, so it's probably story time again. So this one's about slot machines. So what happens if I use a PRNG improperly? What if I don't use it correctly? So there was a casino in St. Louis, and at some point, they realized that they were experiencing bad luck. So usually a slot machine is carefully programmed so that it gives the house a slight advantage. So over the long term, the casino makes money from the slot machine. It pays out less than the people put in. But for some reason, some of these slot machines were paying out way more money than was going in. So these slot machines were losing money for the casino, and they had to figure out what was going on. And what they saw was there were these players who would, I guess nowadays there's no lever, but what they would do is they would put their hand on the lever and they would just hold it for like 10 seconds. And they would be staring at their phone. And then 1 second they would go boom, and then they would pull the lever. And for some reason they would always win when they did this. So it's very strange, right? They would look at this and they'd be like, this is very strange behavior. And then once they win, they would pull out their phone again and then put their hand on the lever and wait and wait and wait and wait and wait. And then at some random time, they would just immediately jerk it and then they would win again. So this was very strange and they had to figure out what was going on. And it turns out they dug into the algorithm and the machines and they found out these machines were using predictable PRNGs. That's a problem. And the reason why is because the output of the PRNG was based on the current time. So at some point they were using the current time as a seed or something, or an input to the PRNG, and that was affecting the output in some way. And if you are someone trying to win money, you take a smartphone, or first you engineer the algorithm and figure out what times you need to pull the PRNG for the best output. So maybe at this point it's being seeded with this time, and this time gives me these favorable numbers. So first I figure that out, and then I just use a smartphone to check the time. And then as soon as it hits the right second, I pull the lever and I win. So that's what people were doing. And a funny story, or side story, I guess, is Las Vegas was not affected by this vulnerability because they have very strict standards. So I think the laws of Nevada actually need to guarantee that the slot machines do not lose money like this, because this is kind of an issue. And this is kind of a fun story. I think there's an article linked, so you can go look at that. So there's another insecure PRNG bug. There are lots of these. This comes up all the time. This one happened because they don't use enough entropy. So that's the name of the program, I guess, that didn't use it. Debian's Linux distribution, that's a crypto library. And I guess the CV is a version or a bug. But basically what they were doing was they were trying to clean up this crypto library, and the author tried to fix how the random numbers were being generated. And what they were using to generate random numbers was they were reading uninitialized memory. So you know how when C memory starts up, there's a lot of garbage in it because it's not initialized yet. So what they were doing was they were actually using the uninitialized C memory as a source of randomness. But this was causing some memory safety software to complain. So the author got rid of it. And now the PRNG was only being seeded with a process ID which only has 32,000 possibilities, which is very easily guessable. So an attacker can just try 32,000 times, and now they have the right number. So if this PRNG was being used to generate private keys because it is a cryptographic library, well, guess what? All you have to do is, if there are only 32,000 different starting states, there are only these many inputs, all I have to do is just try an input. I get a private public key pair, which we'll see later. And if I see a matching public key, then I have the private key. So that was a problem. Okay. One last property that we need from a good PRNG is called rollback resistance. So this property says, if I learn the internal PRNG state, so I know the variables in the algorithm inside, I actually can't learn anything about the previous states or outputs. So this property is kind of maybe hard to wrap your head around, but basically it says, if an attacker learns exactly how the PRNG looks now, they know the input, they know the internal state, right? So they know how any variables inside are working. And maybe a later example will make this clearer, sorry. But if they know the current internal state and they're given a sequence of truly random bits and a sequence that was previously outputted from this PRNG, they can't figure out which is which with probability greater than 1/2. So the way I generally think about this one is you can't go backwards. So if I give you some output and I tell you how this output was generated, so here's the current state, you can't go backwards and figure out what the previous output was. So to me, that's how this property is defined. I can't go backwards. Even if you give me the internal state, I can't go backwards. Now, the security definition, all it said was that the output is indistinguishable from random. It didn't say anything about rollback resistance, so it's not required in a secure PRNG, but it is very useful, as we'll see later. So I guess maybe now, here's an example. So Alice uses one PRNG to generate a key and the IVs. These are all random values, and she uses the same PRNG. Well, maybe later, Mallory compromises the internal state of the PRNG, so she figures out how it's working. And if the PRNG is not rollback resistant, then she can look at the previous PRNG output because the IVs are public, and she can go backwards. And if she goes backwards, what does she get? She gets Alice's secret key. So that could be a problem. Okay, so we do have one example. There are lots of different PRNGs, but one example that's related is called HMAC DRBG. And as you might guess, it's based on HMACs. So the idea is, we saw last time that HMAC output looks random because it's based on a hash. So if I don't know the input, the output just looks like randomness to me. But that's what I want in a PRNG. So let's use HMAC to build our PRNG. So HMAC takes in 2 arguments. So we're going to use 2 local variables as internal state. And we'll just call them key and value to make them easier to distinguish. Okay. So here's the algorithm. I don't think you have to worry about the specifics of this algorithm. So we're not going to test you on why this algorithm works or how it works. But all you really have to notice is that this seed algorithm, well, first of all, the internal state is 2 different variables, K and V. And the seed algorithm just runs HMAC a bunch of times because what it assumes is that the HMAC output looks random. So I initialize the internal state to 0. I use my S, which is my secret input, my truly random input, my seed, to generate some truly random seed internal state values. And so this is the seed function. Okay. Then we have a function called generate. And this one, again, you don't have to know the specifics, but the idea is basically the same. So I run HMAC a bunch of times to generate some random looking output, and then I just return it as output. And if I need to, I update the internal state. So this is generate. Again, I'm just running HMAC a bunch of times. So all you really have to know from these 2 slides is that the actual algorithm of HMAC DRBG, it really is just calling HMAC over and over and over again to generate lots of randomness or pseudo randomness. Okay. And the security of this, it can't be proven. So as long as HMAC is secure, then HMAC DRBG is secure and it's rollback resistant. You don't have to worry about the proof, but the idea is if you've broken HMAC DRBG, you've also broken HMAC, or you've broken the hash. So assuming the hash is secure and so assuming HMAC is secure, then HMAC DRBG is also secure. So we're kind of building our way up in terms of security proofs. And the intuition for the proof here is if I can distinguish that, oh, this is PRNG and this is random, right? If given those two strings, they can figure out which one is which. Then what you've basically done is you've distinguished HMAC from random. And we know from last time that you can't distinguish HMAC from random. We also learned that if you derive old output from the current state, so if I give you the current state, which is I give you K and V, which are internal local variables, you can't go backwards. Why? Because K and V are set with HMAX, and HMAX are based on hashes, and you can't reverse hashes. So if I can go backwards in this DRBG, even if I get K and V, then what I've done is I've reversed the hash underneath HMAC, which I know that I can't do. So that's the general intuition, but you don't have to worry about the actual proof. Okay. I think the last thing we'll talk about is hardware PRNGs. So modern CPUs generally have some functions that generate truly random data. And again, they use CPUs, circuits, or keyboard typing or something. And recall that this is slow, this is expensive. So I think we talked about this, but basically we use true randomness to seed a PRNG, and the PRNG, what? Oh, I think I messed up. Okay. So let me try that again. So modern CPUs have functions that generate truly random data. And so what I do is I use my true randomness, which is my lava lamp or whatever. I seed a hardware PRNG. So this is a PRNG that is implemented on the CPU circuit. And then the CPU circuit returns that in its hardware randomness function. So that's a little weird. Maybe Nicholas can explain this, but basically, I think the idea is just that PRNGs can be included in hardware, maybe. I think we were debating on whether to keep this slide, but yeah. How about let's just say you don't have to worry about this for the exam. Sound good? Okay. And we'll go back and figure out what this means. I think we've made it to the end of PRNG. That was kind of a marathon, and I probably should have stopped for questions, but does anyone have any questions? Okay, because this is one last example. So if you have questions, feel free to raise your hand or shout them out, and I will just talk about this last example. Oh, someone has a question. Go for it.
Yeah, so about the example with the slot machines, did it have to be like an inside guy? Like, how was he aware of this algorithm?
Oh, that's a good question. So how did the attacker know that the slot machines were using this insecure PRNG? So
yeah,
remember,
and can you tell me again what kind of PRNG it is?
Sorry, what kind of?
You said, how did the attacker know to use this something PRNG?
Right. So this goes back back to lecture 1, because lecture 1 said Shannon's maxim: assume the attacker knows the system. So in this case, if you assume the attacker knows the system, then they can figure it out. And in real life, this turned out to be a correct assumption, because these machines, I think they were produced in Russia or something, but basically these were very old slot machines apparently. And so it was very easy to go on the market and just buy one yourself. So what the attackers did was they just bought their own slot machine, and they could take that apart and figure out what was going on. So I think that's how they got the algorithm. And it just goes to show that you have to remember the attacker always knows the system. It's just a good assumption to make, and it's basically always true. Okay. That's an interesting question though. And I think if you read the article, they talk more about it. Anything else? Okay, I think there's one last story. PRNGs have so many stories because it's just so easy to mess up, but here's one last one. This one was in a Rust library. Rust is a memory safe language, but they have a secure random number generator function, but apparently it's not actually secure. And the reason why is because there was, I don't know, basically it just had a lot of problems with it. I think we'll talk about stream servers later, but basically there was no reseed function. So you couldn't even throw an extra entropy after you were done. The seed didn't have enough entropy. It only took 32 bits, which you can guess, and there was no rollback resistance. So that was kind of a problem. And I think the takeaway here is just when you're using PRNGs, it's very easy to mess up. So make sure you use a secure PRNG. I don't know why those are question marks, but I guess those are things you can think about. But make sure to use a secure PRNG. If you have random input, just toss whatever you have into the PRNG, because it can't hurt, it can only help. And I think that's the takeaway. Okay, I guess we have another one for, it's basically the same idea. You get the pattern. It's always the same thing. The PRNG is bad, so guess what? You can figure out the password reset link. So remember how if you want to reset a password on your website, they usually give you this long random looking link, and then you click on that, and then you reset your password. But guess what? If that random link is generated with an insecure PRNG, you can predict that and take over whatever account you want. So that's a problem. There are probably others. Okay, one last thing, I guess, is a quick application. You'll see this in project 2, so I won't spend too much time on it. But basically, you can also use randomness to uniquely identify objects. So if you have a set of objects, like a bunch of files that you have to assign a unique name to every single file, then what you can do is I can just assign a random 128-bit number to each file. And why does that work? Because the probability of generating the same random 128-bit value twice is basically 0. It's just too astronomically small. So generating random numbers, you can basically guarantee that you're generating unique numbers every time. So that's one thing you can do. So you'll see this in project 2, but the way to generate a unique ID is to seed a PRNG and then just generate a random value. And it's astronomically likely, basically guaranteed, that that value is unique and hasn't been used before. Okay. Now I think we are finally done. I know we have stream ciphers. Okay, should we do this before or after the break?
We're about halfway through. Why don't we take a? Do we have time for a break? We have time for
maybe
a short break, maybe a 3-minute break till 4:25.
Okay. Okay, and we're back, and we're talking about stream ciphers. So let's talk about stream ciphers quickly. So the idea of a stream cipher is this PRNG gives me output that looks random. Well, there was one more application of randomness that we haven't covered yet today, and that's the one-time pad. So what if I take this output that looks random and the attacker can't predict it, and I use it as a one-time pad key? That seems like a reasonable way to build a cipher. So that's what a stream cipher is. It's just a symmetric encryption algorithm, and the way it works is it uses pseudo-random bits as the key to a one-time pad. So here's a algorithm, or here's a diagram of it. Basically, Alice and Bob both seed the pseudo-random number generator with the same input, which is their key. And then whatever the output is, that is used as a one-time pad. So I take the plain text, I XOR it with the PRNG output, I get ciphertext. And then Bob takes the ciphertext, XOR it again with the same PRNG output because it's deterministic, and then gets the plain text back. Now, what if I want to encrypt multiple messages? Because remember, one-time pads are not secure if I reuse the key. So here's the fix. The fix is first, Alice and Bob share an IV. This is a public value that they both share, and it's a random value. Yeah, and then what they do is they seed the PRNG with the key and the IV, and that provides the pad that they use for their one-time pad. So that's another way to encrypt things so that you're not reusing keys. Okay, and if you squint really hard, you can actually notice that CTR basically is a stream cipher. That's pretty funny. And the reason why is because this block cipher output is pseudo-random, and we're using the pseudo-random block cipher output as the key to a one-time pad. So stream ciphers, AES CTR actually is an example of that. Now, in terms of security, remember, one-time pads are perfectly secure, and also NCPA secure if I don't reuse keys. And assuming the pseudo-random output is secure, then the stream ciphers are secure. Someone noted that, yeah, you do have to seed a random number into your random number generator. Yes, so yeah, this is definitely a little bit funky, but the idea is that I think this IV can just be generated maybe with the PRNG. I'm not too sure how it's generated now that I think about it. But the idea is that you take this value that's different every time. Maybe it's not even random, it's just different every time. And you seed the PRNG with a different value every time. And that creates a different pad output. Maybe the IV can just be a counter and just tick up. I'm not too sure, but I don't think you have to worry about it too much. Basically, the idea is that as long as you understand that PRNGs, you seed something, you seed a PRNG with the same value on both sides, you get some output, and then you use that as a one-time pad key, then I think you're good to go. And this is just one way to make it so that you're not reusing keys. It's just to add a counter or something different into the PRNG. But yeah, that's a very good question. Maybe we can talk about it afterwards. Okay. So again, stream ciphers are secure, assuming that the PRNG output is secure and it's not predictable and it looks random. And in some stream ciphers, if you encrypt too much plain text, it does leak security because PRNGs sometimes, if you ask it to generate way too much output, it actually starts looping around, which is kind of a problem. But for example, in a CTR, the counter can only go up so high. So if I encrypt so many blocks that the counter wraps around back to 0, then I'm going to start reusing keys. So that's something you might have to watch out for if you're encrypting a gigantic amount of plain text. And I think the question was just that was asked in chat was the PRNG seeding with an IV basically says I have to use a random number to seed the PRNG, or maybe a pseudo random number to seed the PRNG, which is a little bit weird. I guess you can also use true randomness as the IV, so it's not that big of a deal. But yeah. Okay. Yeah. So do limit yourself when you're using the stream cipher, because if you use too much, sometimes the keys start wrapping around. So it's good to limit yourself there. Okay. And the benefit of a stream cipher over the other encryption modes we've seen is that it's kind of efficient. It's efficient because the PRNG output is just continually getting generated. So if I am expecting, if I don't have my plain text immediately and the plain text is streaming in from somewhere, I'm getting 1 byte at a time as I download it or something, then what I can do is every time more input arrives, so I download some extra information, I just generate more PRNG output, encrypt it with a one-time pad, and I'm good to go. So I can continue running this algorithm as more things arrive, which is nice. Whereas block ciphers generally, because of padding, it doesn't really work well on streams. So as more things come in, I suddenly have to re-pad, which is a little bit annoying. So it's not as efficient. But stream ciphers, really efficient. As something comes in, I just generate some more output, XOR it, and I'm done. Whereas CBC, now I have to think about padding, which is kind of annoying. So that's it. Encryption and decryption might also be efficient in the sense that maybe I get this gigantic ciphertext, 1 gigabyte, huge. But I don't care about most of the ciphertext. I only want the last 128 bytes. I don't even need the rest of this 1 billion, however many bytes. So what do? Well, if, depending on your stream cipher, some of them, you can actually decrypt part of the ciphertext without decrypting the whole thing. So you just skip your way to the end and decrypt what you need. So for example, in CTR mode, you can do that because I just generate the pseudo-random block that I need, which is the ith block, and then I run the XOR and I'm done. So I don't even have to decrypt the rest of the ciphertext. I can just decrypt one little chunk that I need. There's another stream cipher called Cha-Cha-20 that also supports this. HMAC DRBG does not support this though, because HMAC DRBG runs HMAC, so I have to run HMAC all the way up until I find the block that I want to decrypt. I can't just skip my way to an arbitrary block. Okay, now I think we're done with stream ciphers. Any last questions on PRNGs? Sorry, that was kind of a lot. Okay, cool. If there are no other questions, then I'm going to tag out, and Nicholas has 28 minutes, sorry, to speed you through if you want. And we can also just
No, you're good. I think we're all right on time. My turn to get my screen shared. All right. Can you see my screen?
Yep.
All right, just making sure I have the chat pulled up as well. All right, so that concludes our discussion of PRNGs for this lecture, as Perrin mentioned. PRNGs are great for if we need to generate a key ourselves. Let's say we're storing data on our hard drive and we want to encrypt it before we store it. But we still haven't talked about Alice and Bob. We haven't talked about how do they arrive at a secret key? Because if Alice just sends Bob their secret key, then Mallory can just look at that secret key and say, oh, scoop that up, and then they can decrypt all of their conversations. So somehow Alice and Bob need to be able to perform an exchange is what we're going to call it, that allows them to arrive at a shared key without any information being sent that lets Eve or an eavesdropper, Eve, an eavesdropper, or a man in the middle figure out what their key is. So it's a little bit weird, and it was definitely weird the first time I tried to wrap my head around it, but I don't know, bear with me for now. So let's pose a hypothetical example. Let's say instead of sharing a secret key, let's just say they want to share a secret paint color. I don't know, maybe they're artists and they, actually, I can't even come up with a good example of this, but let's say they want to share a secret paint color. what Alice can do is she's going to generate a secret color, and let's just say it's amber for A, just to make it easy to remember. And Bob is going to do the same thing. Bob's going to generate a secret color blue. Next, they're going to agree that, okay, let's just say there's some common color out there that everyone knows, even Eve and even Mallory. We're just going to call it green G. All right. Now, they can't just send, Alice can't just send A to Bob, and Bob can't just send B to Alice, because if anyone's listening in the middle, they can just see those secret colors. So instead, what they're going to do is they're going to mix their color together with green. So Alice is going to create a green amber, GA, and Bob's going to create a green blue, GB. And the thing to notice about paint colors is that it's hard to separate them. If you just gave me a color, I couldn't just like separate out the colors. That's not really something that's feasible or easy, or just something that normal people can do. Okay, so now that we have these public colors, let's just call them that, they're going to send them to each other. They're public, so let's just say it's fine for Alice to send it to Bob, and it's fine for Eve to look at it. Alice sends GA to Bob, Bob sends GB to Alice. Okay, so Eve knows GA and GB now. So again, assume that it's hard to separate colors. And the final step that's going to happen is, now that Alice has received GB, this green blue, she's going to mix in her A and then form green amber blue, which I think as a color doesn't actually even make sense anymore, but let's just call it GAB. And Bob, again, he knows GA, so he can mix in his B to form GAB. Now, look at what we've done here. Alice and Bob both know GAB. Alice never learned what B was. Alice didn't know that Bob's secret color was blue, and Bob didn't know that Alice's secret color was amber, but they still arrived at this GAB. And once they have the same color, they can paint their secret painting with secret colors. I don't know. It makes more sense when we start talking about it mathematically. But the key here is that Eve only knows G, GA, and GB. And there's no way to make any combination of this that would let her learn what GAB is. The closest that she could maybe get is green amber, green blue, GA, GB, by mixing GA and GB together. But this is not the same color. There's no way for her to separate out A or separate out B in order to actually be able to learn what the shared secret is. Here's a picture of Evan vomiting some colors because this slide is a bit colorful, but hopefully the metaphor sort of got the point across. We can mix our secrets with something public in order to conceal it from Eve, but still let Bob, the other party, derive a shared secret. So separating paint mixtures is hard, and we have a mathematical version of this. We're going to say that everyone knows a large prime number, just call it P, and a generator G. You don't need to worry about this generator thing too much. Just assume that it's some number that's between 2 and P minus 1, just some number smaller than P. Okay, this brings us to something called the discrete log problem. We have our P and we have our G. And the discrete log problem says that if we have some G to the A mod P, it's difficult to find A. So if you just gave me G to the A, I can't somehow reverse that. I can't take that A and learn, oh, A is actually 5 or 2 to the 20 plus 4. I don't know. I am stuck with only having G to the A. And this is closely related to what we're going to call the Diffie-Hellman problem. This entire thing is called the Diffie-Hellman key exchange. If someone gives you G to the A and G to the B, it's difficult to find G to the AB mod P. When we go into the exchange, this G to the AB is going to be our secret that Alice and Bob share, but that Eve can't learn. So we're going to assume that this problem is difficult. And sort of the intuition to work with here is that the best way we know of right now is, given G to the A and G to the B, try to reverse one of them. So you can find either A or you can find either B, and then calculate either G to the B to the A, which is G to the AB, or G to the A to the B, which is also G to the AB. This is the best known algorithm. There could be a better algorithm, but no one knows of it so far. So we're going to say for now that the Diffie-Hellman problem, basically breaking this key exchange, is at most as difficult as the discrete log, and currently, as far as we know, is as difficult as the discrete log problem. All right. Yeah, side note, if you multiply the values together, so multiply g to the a and g to the b, if you remember your rules of exponents, this gets you g to the a plus b, which kind of looks like g to the ab, but is not actually related to it in a way that is useful to Eve. All right, now that we have our bases, we can put it all together. I couldn't make animations for this slide, so you're sort of going to get it all at once. Sorry. But this sort of follows the timeline of everything that's going to happen. In the center, we have everything that is public. So Eve is here listening. Eve, Alice, and Bob all know that the public parameters just for this algorithm are G and P. P is our prime number. G is our generator, which is smaller than P. Okay. Next, Alice is going to generate her A. I've called her to Amber again, just to remind you of the previous slide. And Bob is going to generate his B. These are just completely random numbers. And Eve doesn't know these because they're generating them locally. And we're assuming, let's just say that they're using a secure PRNG to generate these or something. Okay. Now, again, Alice can't just send A because then Eve would learn it. So instead, what Alice is going to do is Alice is going to raise this G that everyone knows to the power of A, and she gets G to the A mod P. Likewise, Bob is going to generate G to the B, and now that they have these public values, G to the A and G to the B, they're going to send them to each other. So these have gone through the public space. Now Eve knows what G to the A is and G to the B is because they had to send them to each other in order for the other party to learn what this value is. So once Alice receives G to the B, she is going to calculate G to the B, and then she's going to raise that thing to the power of A. So keep in mind, Alice never learns what B is. Alice also only has G to the B, so she can't go back and derive B as well. That would be breaking the discrete log problem. But she can raise it to the power of A. And if we follow our rules of exponents, we know that something to the power of something all to the power of another thing is something to the thing times the other thing. I'm not very good at describing it in words, but basically G to the B, if she raises that to the power of A, that'll get you G to the AB down here. And Bob's going to do the same thing. So Bob's received G to the A. He can raise that to the power of B, even though he'll never actually be able to learn A. And he's going to arrive at this same number, G to the AB. And at this point, Alice and Bob have their shared secret. Alice never learned what Bob's secret B was, and Bob never learned what Alice's secret A is, but they've both still managed to arrive at the same shared number in a way that Eve can't get to. So Alice knows A, so that lets her derive G to the AB, and Bob knows B, so that lets him derive G to the AB. But because Eve only knows G to the A and G to the B, and I guess also G and P, there's no way to combine these two values in order to arrive at G to the AB. Again, the best that she could do is G to the A plus B, but mathematically that's not actually related to the original number. So when I first learned this, I was like, I feel like this should be more complicated because it's like somehow there's through this mathematical mod math magic, I can arrive at a shared secret with someone else, even though no one in the middle can possibly learn this. So I think this is a really cool key exchange, but are there any questions on how this works before I continue? Could you use some other method here? Yes, we're gonna get to that in a very short moment. Not necessarily one-way and commutative, but, or actually, I'd have to think about one-way and commutative, but yes, there are definitely other mathematical groups you could use, which I'll get to in a moment. So one thing that you can do with the Diffie-Hellman exchange is you can use it ephemerally. When we do this, we call it Diffie-Hellman ephemeral or DHE. If you ever see DHE around, that's what it stands for. Ephemeral just means that something is short-term and temporary, so it's not permanent. This might be useful because if I want to talk to Bayron and I want to use a different key each time, I can use a Diffie-Hellman, and then each time we communicate, we have a new key going on. So if someone learned what my last key was, they can't decrypt our communication for this key and for this communication and so on and so forth. In a ephemeral key exchange, Alice and Bob are going to discard AB and their secret key G to the AB. So they'll erase it from their memory. They'll never even have saved it, so no one can possibly recover it. Because you need either A or B to derive K, this means that no one can ever actually derive K again, assuming that the discrete log and the Diffie-Hellman problems are hard. The only thing that's left is Eve's G to the A and G to the B, the things that were sent publicly. But again, you can't get back to the original key. When we use an ephemeral key exchange like this, we call it a session key because it's only used for an ephemeral session. That's a typo. But yeah, the best benefit of this is forward secrecy. So usually you can assume that Eve is not only listening to everything that you're saying, but is also recording. So we can assume that Eve will, I don't know, she has a large warehouse somewhere just full of hard drives that contain everything that she's ever listened to. And if later on she can learn something that allows her to decrypt encrypted communications that she listened to a while ago, then we say that this is still insecure. So if Alice and Bob use Diffie-Hellman ephemeral, if they use a Diffie-Hellman to agree on such a key, and then they use K as, say, a symmetric key to a block cipher, and then they discard A, B, and K, as you do for an ephemeral session key, then if Eve later breaks into Alice's computer or Bob's computer, this still doesn't give her the ability to decrypt the messages that she's saved in her warehouse somewhere. Nobody saved A, B, or K, so the only thing that Eve has left is G to the A and G to the B. And obviously this means that Alice has to find some way to dispose of it securely, and sometimes there can be security issues with regards to that, but we won't get into that. We're just going to assume that once you delete it, it's gone forever. So once Eve breaks into Alice's computer, she doesn't learn anything useful. She still only knows G to the A and G to the B. So those communications that Eve recorded a year ago in her warehouse remain encrypted, and nobody can ever decrypt it ever again for the rest of time until the Diffie-Hellman problem is broken, at least. All right, does this make sense? Forward secrecy? This is something that's used in messaging apps a lot. It means that if someone breaks into your phone, they can't decrypt past messages if they're recording them. So we'll get more into that when we talk about Signal as well. Okay, as pointed out in chat, you don't have to use exponentiating in a it's complicated. You don't have to use, say, the discrete log problem. There are other ways that you can do a Diffie-Hellman as well. You can just sort of think of it as the discrete log problem is hard because when you exponentiate an integer, if you think of mod math as like a clock and you exponentiate something, it just goes around and around and around and it lands somewhere completely else. It's unrelated to the original value, which is why it makes finding that A and G to the A so difficult, because it goes around and around and around and it lands somewhere completely random. We can actually generalize this to any mathematical group that has this property. So this is all math stuff that you don't actually need to worry about. But formally, the discrete log that we just taught you is the discrete log under the multiplicative group of integers mod p under generator g, which is a lot of words that you don't need to understand. But again, the intuition is that because it wraps around, it makes it difficult to recover the original value, the original exponent. So we can actually do this on something else. If you've heard of elliptic curves, because sometimes that's a crypto buzzword that gets thrown around, they're really just a curve. There's an equation for the generalized form of an elliptic curve. But one of the keys of elliptic curves is that if you have an elliptic curve and you add a point to itself, don't worry about what it means to add 2 points, but basically you can jump around this curve by adding a point to itself. And if you jump around it enough times, it's hard to figure out what that original value of the point was. So repeatedly adding a point to itself on a curve is another cyclic group. It has the same wrapping around property where if I add it enough times, it'll go back to its original value. So again, you don't need to understand the math behind this, but what you will often come across is something called the elliptic curve Diffie-Hellman. So this is abbreviated ECDH, as I've shown on the slide up here. And its hardness is based on something called the elliptic curve discrete log problem, which is just the discrete log problem, but on elliptic curves. And the primary reason we use this, because it's so much harder to understand, why on earth would anyone want to, elliptic curve things, is that it's sort of harder and it's easier to create keys. And what this means is that you can have a shorter key that has the same amount of security. So there are a couple numbers that you can find if you look online, but if you have a 3072-bit normal Diffie-Hellman key, so just a really large number mod p, this has the same security as a elliptic curve Diffie-Hellman key that has only 384 bits. So we have a smaller key. This means it's easier to store, to transmit, so on and so forth. It's just easier to deal with, at least when it comes to implementation. So this is why we use ECDH. Questions on this? All right, and there is one computationally faster than the other? Yeah, elliptic curves are actually, I know they're faster than RSA, and I think RSA sort of is based on the same exponentiating thing as Diffie-Hellman. So yeah, generally elliptic curves are faster, one, because the keys are shorter, and two, just because the math that goes into it, I think is easier to implement. I don't know too much about it, but I know in general it is faster. That's another positive reason why. The main reason why you don't see it in as much use is just because it's not as widely supported, because it's a newer sort of mathematical discovery / standard. So yeah, but it is slowly becoming more and more common. And I'd love to talk about some other alternatives to elliptic curves after lecture if you want. All right, but we do have 9 minutes, so let's try to finish up these slides. So this is great for Eve. If Eve is listening on this conversation, there's no way that Eve can recover the secret key. But what about Mallory? Is there anything that Mallory could do if she wanted to somehow continue to be a man in the middle between Alice and Bob? Can you think of an attack that Mallory might perform? Give you 10 seconds to think about it. There's one key thing that's missing from this exchange that would allow, sort of, maybe not mess with G to the A per se, because that still doesn't let her learn the secret value she needs. There's also something about generating A and B. I'm not entirely sure what that's referring to, but yeah, man in the middle. She's going to now exploit her abilities as a man in the middle to mess with Alice and Bob. So remember, Mallory is allowed to alter messages and block them and send her own messages. In fact, Diffie-Hellman is not going to be secure against a man in the middle, because what Mallory can do is she's going to literally sit in the middle of this communication. And then Alice is going to perform a Diffie-Hellman with who she thinks is Bob, but is actually Mallory. And then Bob is going to do a Diffie-Hellman with who he thinks is Alice, but is actually Mallory. So here's a diagram of it here. Remember, Alice has no way of verifying who she's talking to. There's no authenticity in this protocol. So Alice does what she does before. She generates A and sends G to the A. But Mallory is going to intercept this. Alice doesn't know who she's sending it to because there's no authenticity. So Mallory receives G to the A. And then she also has her secret M and calculates G to the M. Alice receives G to the M, but has no way of knowing that this is G to the M instead of G to the B, because they're all just numbers. And then Mallory is going to end up driving G to the M to the A, which is, this is a little bit wrong. This is G to the AM. And then everything happens the same way with Bob. So Bob sends his G to the B to who he thinks is Alice, but Mallory intercepts that and sends her G to the M instead. So now Mallory has two keys. Mallory has one key to talk to Alice and one key to talk to Bob. And if she wants to remain hidden, what she can do is oh, I've received a message from Alice. I'll decrypt it with my G to the AM. I'll read it and, I don't know, mess with it or something. And then I'm going to re-encrypt it with my G to the BM and send it to Bob. And now Alice and Bob have no idea that they're being attacked because from their perspective, everything's being encrypted with the secret key that they derived. Does this attack make sense how this works? Any questions? All right. So we're like almost there. This is almost perfect. We almost have a way of communicating without letting anyone interfere, but we're not going to be able to solve this problem today. So as we've seen, Diffie-Hellman is not on its own secure against a man in the middle. Some other issues that we have is that Diffie-Hellman is an active protocol. This means that Alice and Bob both need to be online. Alice and Bob both need to generate their secret A and their secret B. And if Bob is, I don't know, not connected to the internet on a plane or something, there's no way for him to generate his B, and he can't give that to Alice. So Alice is sort of stuck and they can't arrive at a shared key. We'll look at how to, basically instead of a Diffie-Hellman, we'll create some protocols that allow Bob to just give Alice a key and then go away for the rest of time, and Alice can still encrypt things. That will be, I believe, next lecture. And the other thing, as I mentioned, is that Diffie-Hellman doesn't provide authenticity or authentication in this case. It's the same thing. As Mallory performed in the previous slide, she just sat in the middle and did a Diffie-Hellman key exchange with Alice, even though Alice thought she was exchanging with Bob. So Alice has no way of knowing who she's actually doing a Diffie-Hellman with. And in the next lecture, we'll sort of solve this as well. So that brings us to the end of today's very dense lecture. Thanks for sticking with us. Just as recap, oftentimes in crypto, we want random numbers. It's hard to generate random numbers, I guess, unless you have a lava lamp. Otherwise, it's really slow. So instead, what we have are algorithms that let us take our small amount of randomness that we can generate and create a lot of seemingly random bits from that small amount of randomness. There's a way to seed the PRNG. There's a way to reseed the PRNG if we want to mix more entropy in. And of course, there's a way for us to generate seemingly random bits from our PRNG state. We need to make sure that such random bits still look indistinguishable from actual random bits. And one additional property that we want is that the adversary can't go backwards. So obviously it'd be a bad thing if they could go forwards, but we also don't want them to go backwards because maybe we derived some keys earlier. So we don't want the adversary learning that even if we compromise our internal state. HMAC DRBG was the construct that we introduced you to, but there are a couple others. And one application is in unique identifiers where you want something to be identified with an ID that is unique to the entire universe, basically. When we started talking about key exchanges, the algorithm is Alice chooses A, sends G to the A to the Bob. Bob chooses B, sends G to the B to Alice, and then they derive a shared secret G to the AB, which they can use for their future communications and which is safe from anyone who's listening, eavesdropping. This provides forward secrecy. So if Alice and Bob delete their secret components, A, B, and K, then nothing is saved and there's no way to ever recover what the original value of the key was. You can also do this over other mathematical groups. And the one that you'll see most commonly is the elliptic curve Diffie-Hellman. And some issues that we went through is that it's not secure against man in the middle. So Mallory can just sit in the middle and do a Diffie-Hellman key exchange with both sides. Both parties have to be online, so it might be really inconvenient if you want to, say, send a text message to someone who's on a plane. And it doesn't provide authenticity, which is why Mallory can sit in the middle and perform her man in the middle attack in the first place. And yeah, that's it. Are there any final questions before we head on? Now that I'm looking at it, I'm realizing the question of how to generate A and B might have been a question and not an answer to the question. You would just use like a PRNG or something to generate a random number. All right, if there's nothing else, I'm going to stop the recording and everyone enjoy the rest of your week. If you haven't finished project 1, I actually don't know.
We have
where-
office hours, so
Yeah, we
stop
have
by
office
and-
hours. That's where I was going with that.
Yes,
All right. See you, everyone.
it's not too late. It's a little late, but it's not